So another good morning. Actually, this is a lovely place, you must have noticed. It's my third time here, so it's really great to be here. And we had previous great schools, but still, let me re-emphasize something Dario just said. You know, some speakers, myself perhaps included, tend to go a bit fast at times. And then you have two options. Number one is to fall quiet. And I've seen that happening here repeatedly. So that's a bad option. Yeah? The good one is to really start asking questions to slow the guys down and, if necessary, aggressively ask questions. I mean, really, don't let the question asking be done by the usual 2 or 3 people who always ask questions, but join forces. Everybody should ask at least one question during this week. Yeah? Please do that. And I'm saying this in this pronounced way because really we have, I've seen the opposite. So please let's not have that. Yeah? And you will see it. It will become necessary at times to tell people that they have to, or they are just incomprehensible, which also happens. Yeah. Good. So on that note, it's about topological matter, the whole school, and perhaps the first thing to realize is when we talk about topological matter, we actually have not so much of an idea of what we are talking about as of 2018. Yeah? So that we know by now that there is a universe of topological quantum matter out there, but we can't say to understand what we have and what's going on. What we do understand is that there are different life forms of topological matter, and some are understood somewhat better than others. And this being so, it's good to start perhaps with introducing some organizational principles or some fundamental parameters which serve to discriminate different types of topological matter, various of which will appear here. And let me introduce for you in kind of an 8-fold distinction scheme, which I find is useful. So when we talk about can you read this? Yeah? Topological matter. I have lecture notes. You don't have to take notes. We can communicate to you via some electronic channel. Yeah? So don't bother to write it. Okay. Matter. So here, there's others, but here are 3 very important schemes of distinction. Number one, this is, informal way I'm writing it, but we have to ask what is the nature of the fundamental particles on which our matter is built, and the prime distinction here is whether we are talking about matter that is fundamentally bosonic or fermionic. You know, topological matter is prone to generate all kinds of weird quasi-particles, but still, at the very basics, you can ask yourself, am I dealing with a system of fermions on the microscopic level of bosons? That's important. So, this is the distinction we want to make. Second principle is we should ask ourselves, is the system we are talking about, is it gapped? Does it have an excitation gap? Like, I don't know, an insulator? Or maybe it's fundamentally gapless, metallic in a fermionic case, for example. Yeah, this is another distinction. So is there a quantum gap present? Yes or no. And the third is to what degree is our system influenced by particle correlations and interactions? And this is naturally, by nature, it's a soft question I'm asking, but in a modern way of saying, you might ask, how much entanglement do I have in my quantum system? And am I talking about a strongly interacting, correlated, long-range entangled system, or a weakishly interacting system which is only short-range entangled? Yeah? And I'm not bothering to give you a formal definition of entanglement here, but you feel me. I mean, it's about strong or weak interaction. So entanglement. Say here, strong or weak. And that gives us 8 different opportunities, and they often serve as a good starting point. The way I understand it, the focus at this school will be on the physics of fermionic quantum matter that is gapped and weakly entangled. That includes topological insulators, superconductors. Occasionally, perhaps we will talk about gapless systems, and we have Dirac quantum matter on board, like Weil system or so, more or less this type of physics. Yeah? So I guess the focus, not exclusively, will be here, here, and here. And that's a relatively simple class of topological matter. Okay? Now, staying on this abstract level, I mean, suppose we have, I don't know, we have a system that belongs to this class. I mean, some kind of nominally fermionic system with a gap. So we're focusing on a gapped situation, an insulator, if you want. And interactions can be there, but they're probably not too strong. And we have reasons to believe that the system is topological in a manner which will be explained not by me, but by Titus, for example, in the next lecture. But maybe there is some topology going on. Yeah. Now we can ask ourselves, what are the physical principles, or what kind of physical mechanisms are essential to understand? And we have to get under control to understand the physics that's of interest to us. It's again a weak question, yeah? But for example, it stands to reason that we will not bother about the details of individual matrix elements or some kind of fine structure analysis of the dirt that is present in the system. It's about topology. Topology, we know, is a very robust, I mean, it's by definition robust, yeah? Very robust physical principle. So we can ask ourselves, what kind of physics do I need to understand about this system or the quantum Hamiltonian underlying the system if I want to do topology? Any suggestions? What is relevant? I'll give you another hint. I mean, topology means it's global physics, yeah? I mean, the system is by definition a global property. So when we probe a global property, and think of yourself, you are an electron in the system, you have had enough time to explore the entire phase space of the system, yeah? You need to feel it all in order to sense topology being present. So we are, in some sense, we are doing long-range, long-time physics. So what kind of physical principles are relevant to this extreme limit, or in this universal long-time limit? Any suggestions? What do I need to understand?
Maybe band structure.
Band structure is yes, but that's already a good answer, but it's even less detailed, more general. Symmetries, very good. Symmetries is a prime candidate. The symmetries of the underlying Hamiltonian is one of our, I mean, this is, we really get to understand this. Symmetries. Symmetries. Well, the second one going along with symmetries I give you is of course topology itself. This all has to be defined. Yeah, what is topology? How do we describe it, and so on? But this is the second one, and there is a third one. What is the third? Any idea? Symmetry, topology. Quite obvious. No? Equal level of generality. Yeah? Hmm? Yeah, very good. Brilliant. Dimensionality. That's the third one. So we have dimensionality. Now you can argue all matter is essentially three-dimensional, but you know we are doing low energy physics, and at low energies, something like a two-dimensional electron gas, which has a microscopic extension in the third dimension, often behaves effectively two-dimensional. Yeah? Or you have something like quantum wires, which still have a nominal, they're not mathematically one-dimensional, but at where low energy physics is regarded, we very often can treat them as one-dimensional. So these three are the most important, arguably the most important principles we need to keep to focus on. And I'm the symmetry guy. So what I will do in these lectures is I will talk a lot, almost exclusively, about how to understand symmetries of quantum matter in reasonable generality. There will be zero topology in my lectures. Actually, I have 3 lectures. And the plan is like this. For symmetries, I probably need 2 or 2 minus epsilon of them. Yeah? And that leaves a third lecture, which comes on Thursday, I mean, deep into the school. And what I will do on Thursday is still up for decision or perhaps even discussion. I mean, I will tell you a little later what the options are. Yeah. So there will be some different yet related subject, but now it's about symmetries on a very, very basic level. The reason being that, in my experience, I stress this now, the understanding of symmetries is essential, but it's also somewhat prone to confusion. I mean, there are several spots where one can get easily confused, and it's really good to have a good fundamental basis to understand symmetries in this context here. So, symmetries. So we start in very basic ways. Ideally, this should be textbook, it is textbook level, but much of this will be familiar to you. Symmetries really on a general level in quantum mechanics. So let's forget all this topology stuff and so on, but really go start on a very general basis and start from the following data given. We need a Hilbert space. We want to do quantum mechanics. We have a Hilbert space. At space H. And for definiteness, I give it a dimension, but you can send the dimension to infinity. Yeah? So, but sometimes it will be good to talk about finite dimensional spaces. And in this space, we have quantum states psi. Yeah? There is a linear operator acting in this space, which is the Hamiltonian in the first place. Some linear operator represented in H. And now it comes, I mean, the most important actor now in this context here will be a symmetry group. G, and it contains elements G. Now, symmetry groups, you will see lots and lots of realizations of different symmetry groups in this week here. Some of them are discrete. I mean, think of fundamental symmetries like parity symmetry, which is a Z2 group, or there can be crystal point groups. There will also be continuous groups, like rotation groups, so it's wide open here. Yeah? We have lots of different groups which stand in the background. And these groups are represented in the sense of group representations in the Hilbert space, which means the following, that the symmetry group is represented in H through mappings like we take a state and we take a group element. We have a group representation that means typically a unitary representation means think of a certain rotation, and it induces in my Hilbert space a rotation, say, acting on a spinor or I don't know, a wave function or whatever. Sometimes people write here some other symbols, rho G, in order to stress this representation character. But what really matters is that group elements induce linear mappings in the Hilbert space. Yeah, so far good? Okay. So that's the general starting point. Now, at this point, now we're at a crossing. We have to discriminate between or distinguish between two fundamentally different types of symmetries, and both will be equally important in this week. I mean, you will see that. And these are unitary and anti-unitary symmetries. Yeah, this is a very important distinction. The thing is that most symmetries, most in a weak sense again, in quantum mechanics, in QM, are unitary symmetries. Which simply means that if you pick an abstract group element of whatever group you're interested in and consider this map, which is induced, this will be a unitary map in our finite dimensional Hilbert space. This is a unitary symmetry. Yeah? So examples are the usual suspects: parity, rotation, translation, whatever. These types of symmetries. Unitary symmetries, yeah, let me write them. Translation, crystal point groups, very important. Point groups. Rotations and whatever. I mean, this type of stuff. Okay. And it means that, by definition, that for unitary symmetries, G is an element of the UN in our Hilbert space. Yeah? And this set of symmetries now has to be complemented in order to understand the physics of topological matter by anti-unitary symmetries. Anti-unitary symmetries are a complementary set of symmetries. So they exist anti-unitary symmetries. Anti-unitary symmetries. And this means, then again by definition, that G, which in this case I will denote by theta, just to distinguish it. It's just a symbol, yeah, a name, is an anti-unitary map. And I'll recap in a second what anti-unitary maps are. Unitary map. And examples here are time reversal. And I will introduce this all in generality. Particle hole symmetries, particle hole charge conjugation. And that's pretty much it. So a bit of history. When the physics of topological matter started out somewhere late 90s or so, yeah, I mean in general, and then peaked for the first time in 2006, the famous work on topological insulators. Our understanding was that anti-unitary symmetries are really key. So this was the most important principle, or there is a famous periodic table which at some point will pop up in this week, I'm sure. And it organizes the physics of topological insulators and superconductors according to dimensionality and the anti-unitary symmetries. These are the most important distinctions. Now the situation changed somewhat 2010-ish. In 2010, novel types of topological insulators became fashionable. Crystalline topological insulators, now more recently the higher order topological insulators, which I'm sure Titus will talk about. Higher order topological insulators. Yes, they will come. And they owe their existence typically to unitary symmetries or combinations of unitary symmetries and anti-unitaries. So we really have to understand, and I mean it, we have to carefully be careful in understanding the physics of anti-unitaries, of unitaries, and their interrelation. Yeah? That's why this is the first talk, perhaps. It's very basic material. So unitary symmetries, I trust, are familiar to everybody. Anti-unitaries, maybe not so much, or your understanding has gone a little bit dusted. So let me recap a little bit what anti-unitary symmetries are and spend a while on them. Now, how do I do that? Probably just erase, yeah. The good thing about anti-unitary symmetries is that the set of anti-unitary symmetries is much, much smaller than that of unitaries, and we can organize them neatly into a principle which just involves 10 different. 10 sounds like a large number, yeah? But this 10, as we will see, can be easily understood. So there is just 10 different classes, and that's it, as opposed to the zillions of unitary symmetries we can distinguish. Yeah? So in some sense, they are simpler than the unitaries. So a reminder, what is an anti-unitary map, first of all, in a Hilbert space? So a map theta, for example, is symmetry, which is a linear map from H to, or better to say an antilinear map, from Hilbert space into the Hilbert space, is anti-unitary if, and this is a defining unitary if the following holds. You know, we can just for the fun of it ask ourselves, what is the inner product? We are in an inner product space. Inner product between a state transformed under the symmetry or the map and another state. And if this was unitary, these guys would just eat each other up, yeah? Because theta dagger would be the inverse of theta. And it's almost the same here, except that you catch a complex conjugation sign. So that's with a complex conjugation, which is to say that this equals psi dagger psi. So that is the most important. It's almost unitary except for this complex conjugation. That there is a second property that, and it's related, if you let theta act on a state multiplied by a complex number, you can't pull out the complex number just like so. You catch a complex conjugation again. So this equals that bar theta acting on psi. And what you can then show is that given this, given these properties, we can represent anti-unitaries in a way that is very useful and important in practice. For each anti-unitary, there exists a unitary map, U equals UN, with the property that theta equals that unitary times complex conjugation. And for complex conjugation, I introduce just this formal symbol, yeah? K acts on states by complex conjugating them. So K is complex conjugation. So this is the general math. Now comes a bit of physics, or almost physics. In physics, we usually have the situation that, not usually, categorically have the situation that anti-unitaries of physical relevance square either to 1 or minus 1. Yeah, that's the idea behind this is, if you think about time reversal or such, you reverse time twice. On the level of observables, you want have no effect. On the level of states, you tolerate a plus or minus 1. Yeah. So this is physics. Theta squared equals either plus or minus 1. Identity operation. And prominent examples of realizations of such maps are as follows. For example, if you work in a Hilbert space where relevant symmetry is just complex conjugation, yeah? And that's, of course, very often in practice, theta equals k, then we have trivially complex conjugating twice is 1. Yeah? So this is theta squared equals 1 situation. Another frequently realized situation is that you have you realize this unitary here as a second Pauli. This is and you will see examples of that, I'm sure. Yeah. And if you take that map and you square, you get minus 1. So that is theta squared equals minus 1. In practice, we very often have a situation that if an anti-unitary is important, we try to work in a basis that represents it in the simplest possible ways. Yeah? And these are frequently used representations. I mean, if you have, say, time reversal present and you know time reversal squares to minus 1, you try hard to if necessary, apply unitary transformations to bring your time reversal operator into this form. If it doesn't come like this out of the box, you work a little and try to do that. And that's a practice remark. Good. So that is anti-unitary maps and a few basics on the representation. Any questions up to this point? Yeah? Yeah, you under minimal physical requirements, and I give you a formulation somewhat later of, in a way, I will derive these symmetries from a second quantized perspective, and I can give you then a hint where it comes from physically. You need, yeah, there's a bit of physical input, minimal piece of input is involved. Yeah. Oh God, yeah.
How do you define complex conjugation?
Huh?
How do you define complex conjugation? Do you have a canonical complex structure, or so how do you define?
Yeah, no.
Is acting on the vectors?
Yeah, I guess you trust that you have a canonical complex structure given in your part of your raw definition of your Hilbert space. Okay. Yeah. I mean, probably you can do something more fancy if you want, but actually, is the speed okay, or I can easily speed up? Am I too slow? No? Okay. Good. Yeah. I'm just asking. I mean, good. So now let's use this raw material to come to the actually non-trivial conclusion that in quantum mechanics there are only 10 fundamental different types of anti-unitary symmetries realized. What I mean is the following. You give me a Hamiltonian, some fermionic quadratic Hamiltonian, or need not even be quadratic, I mean some fermionic Hamiltonian, and I put it in one of 10 boxes. And that really nails its content where anti-unitary symmetries are concerned. And appreciate it. This is a great source of simplicity. We have only 10 different options. Yeah? And let's try to understand why there is only 10 different settings of anti-unitary symmetries. Everybody has this, and because I want to send a blackboard. So to do that, there are different ways of getting to this number 10. I'm starting with the quick and dirty and efficient way, yeah? the fastest way to get there, which is, from a physical perspective, somewhat unsatisfactory. You will see that. And I will back this one up in a second discussion, via a more substantial discussion starting from second quantized representations. Yeah? So first comes the quick and dirty way of understanding the number 10. And it goes like this. 10 symmetry classes. We start with a definition. A system is time reversal symmetric and don't attribute too much meaning to this word of time now. It's just a definition of this word. Yeah, forget what time is. It's just a name. Time reversal symmetric if there exists an anti-unitary, and I call this anti-unitary now theta t for time. Just again, it's a label. And we have the property that the Hamiltonian of our system commutes with the operation in the following sense. Inverse equals h. So that is if it was about unitary symmetries, then you would say this is the usual definition of a symmetry, right? You have a unitary symmetry, say rotation. Hamiltonian is symmetric if it commutes with rotation in this sense. Now we say where anti-unitaries are concerned, we declare this here. This is our definition of a symmetry. And there are now 3 different possibilities to distinguish. 3 possibilities. Yeah, here's the symmetry, well, one of the distinguishing principles is, remember, we agreed to discriminate between theta squaring to 1 or minus 1. So we have to ask ourselves, is this a 1 or minus 1 guy? Yeah? Yeah. And then we have the following three options. Either the symmetry is absent, just Hamiltonian doesn't have it, we don't have the symmetry. Then we don't worry about what's going on here. If it is present, we can have here a +1 situation, or if it is present, we can have a -1 situation. And that's pretty much it. And we give these situations labels. We call this one here T0. That's just a name, I mean, a tag for the symmetry. This is a T0 system. This is a T+1 system, and this is a T-1 system. And that makes now, these are three different possibilities we have. Yeah? Quick comment, again, it's a practice comment. Yeah, I want to, so here, let me comment. You may be familiar to the notion that systems, I mean, theta squaring to -1, this is fermion, spin half integer physics. Yeah? I mean, that's a very common notion. If you have, this is famous, if you have spin around, time reversal operator squares to -1. I just want to caution that this is often but not always the case. You can have spinless quantum matter or integer spin which has T-1. And I want to give you one example. So, example of a T equals -1 system without spin. Without spin. And that is, yeah, you can consider graphene. And you know, if you don't know it, I mean, I'm just telling you, graphene has two Dirac cones in the Brillouin zone. So it's a two-dimensional Dirac system, essentially, each cone. And each of these cones can be subject maybe to some potential scattering. Yeah? So then you have a description where each node is described by an effective Hamiltonian. H, maybe there is some potential present. And now we come with a 2D Dirac structure. Px plus I py and px minus I py. And here may be some potential. Right? And now you can convince yourself that H equals sigma y, H transpose sigma y. And sigma y is the second Pauli in this basis. Yeah, you transpose it, P goes to minus P, and then you have to conjugate with sigma y to get the P orders again in the proper place. Yeah, check it. Now you see here, this here is like HT, H is emission, so this is like complex conjugation. And these are two sigma y's sitting here. So that is time reversal symmetry under theta equals sigma y times k. Yeah? So, and this one squares to -1. So, and there's no spin involved here. Okay? So one has to be, has to watch out for such situations. Okay, so that is, these are three different, yeah? No, there was somebody. Yeah, brilliant question. Actually, I'm coming to that in another example, but you can define it. It's actually a brilliant one. You just define this here as a symmetry, and you don't care whether it's a physical time reversal you're talking about, which would really flip this p over there. This little p here is the difference from this k point here, which I'm And I'm just defining this operator. I call it time reversal. Now I'm using that. I need not talk about physical time. And it's an effective symmetry with all the consequences that go with it. Yeah, excellent point. Mm-hmm. Why did it change? So that's where this class of symmetries. Now, like I said, if this was about unitaries, this would be the end of it. But where anti-unitaries are concerned, it pays, and it's physically relevant to consider situations where you have an anti-unitary, which, when it acts on H, produces a minus sign. So that's another class of settings we now distinguish. We call, this is now pretty much mirroring this, but slightly different setting. System is called charge conjugation symmetric. Conjugation symmetric. And again, this is just a formal name tag. Yeah. If there exists an anti-unitary, and now I call it theta c, just again, it's just a name, such that H, when theta c acts on it, theta c inverse equals minus H. So we tolerate an additional minus sign. And very same story. There are again 3 different possibilities we can have. Possibilities. The symmetry can square to plus minus 1, and then we have a situation, it's either absent, in which case we don't care and call this C0, or it is present, we have theta square equals 1, plus 1, and then we call it a plus 1C system, and here it's plus minus 1, minus 1. Good. So this situation is again frequently realized in nature and in the types of systems we are interested in. Let me give you a comment similar to that one here. So when do we have such symmetries? I mean, when do they occur? The name charge conjugation gives us a hint. I mean, very often these symmetries are realized in connection with superconducting matter. Yeah? Which is to say that the realization, physical realization of this setting often requires a particle hole Nambu type structure. Yeah? So I give you one example. Comment. This one over there, C, usually requires a Nambu structure. For example, if you take a plain vanilla superconducting Hamiltonian, like H minus H transposed delta dagger, with some order parameter, and you require that you have this symmetric order parameter. This would be a spin triplet situation. That one is C-symmetric under minus 1. So it you can check that if you conjugate it with Pauli minus 1 times complex conjugation, you get it back with a minus sign. So that is a typical situation where this is realized. like I said, you often need such structures, but not always. I mean, there are cases where you have Hamiltonians of simpler structure, which are charge conjugation symmetric. Just by curiosity, anybody knows an example of a very simple structured Hamiltonian, or whatever simple is relative, yeah, but no? It's not obvious if you don't know it out of the box, but when we're dealing with Majorana fermions, Majorana is very popular these days. Yeah, what's it? Majorana? Yeah, exactly. So Majoranas. Majoranas like real fermions, yeah, and I'm sure you will have examples in this week. Since they like reality conditions, it's then often it pays to transform the Hamiltonian to a maximally, if you want, real form. And in such cases, you often represent your Hamiltonian as I times an antisymmetric matrix. Yeah, I times an antisymmetric matrix. You do basis transformation. It's called Majorana basis. You can transform Hamiltonians to this form, and that one here is charge conjugation symmetric with just complex conjugation. Yeah? You complex conjugate, you catch a minus sign. That's a charge conjugation symmetry. And that somehow tells you that the Majorana came from some triplet superconductor. That's a very basis, but yeah, just mentioning it. Is C equals -1. So now we have how many properties? We can have Hamiltonians which combine these symmetries, right? I mean, so we have here 3 settings, and here we have 3. And we can have now a superconductor Hamiltonian which has some charge conjugation symmetry. And it's also time reversal symmetric in some way. So that gives us, because I mean, we can combine all 3 of them and realize them, so we have 9 possibilities now. Yeah, 3 times 3, 9 possibilities of symmetries. Yeah, perhaps before, no, yeah, let me go on and then I make another comment. So now I'm telling you that this 9 is undercounting. In fact, there are 10 different possibilities. So 10, and the 10 should be read as 8 plus 2. 8 plus 2. And I explain that now, where this 8 plus 2 comes from. Before introducing the number 8, let me give you one more definition. A system is called chiral symmetric. How am I actually doing in time?
You have 15 minutes.
15 minutes, okay, that's perfect. Chiral, or has a chiral symmetry. Some people hate this word symmetry in connection with chiral, but anyway, that's just the name again. Symmetry if chiral symmetric. If it is symmetric under the composition of a charge conjugation and time reversal symmetry. If it is symmetric under symmetry S, which is just the abstract composition of a time reversal symmetry and a charge conjugation symmetry. If that is the case, it is also symmetric under T times C. So the order doesn't matter because you can write this here as T, how do I want to, or let me start with this here, sorry. It's better. I give this TC, T inverse T. TC, and then comes, am I blind? No. Oh yeah, everything is okay. And that here is unitarily equivalent to another C. So this is a C tilde or whatever. Yeah. So I just want to stress that the order here doesn't matter. What does matter is that we have a double symmetry realized. I mean, time reversal and charge conjugation in combination leave the Hamiltonian invariant in the sense of our tables here. Yeah? And so if we have that and just work out what it means, I mean, copy the definitions, then we find that the map theta c, theta t acting on H, theta t inverse, theta c inverse. So time reversal means that this here gives us back H, and charge conjugation means that this gives us minus H. Yeah? So we get minus H. Okay? This is the consequence. But now notice, here we have two anti-unitaries in succession, and they are unitary. This is a unitary operator. How do you see that? The naive way of putting it is there are two complex conjugations here involved, so complex conjugations go out. Yeah? So this is a unitary. This is unitary. And that's why people often don't like the word chiral symmetry, because we have a situation where unitary times unitary inverse produces minus the Hamiltonian. Yeah? So it's somewhat odd, and you can worry about the mathematics. You know that very well. But still, for all practical purposes, it's as useful and important as a symmetry. Only it has to be handled with some more care. Yeah? So there is anomaly physics coming in and stuff like that. Yeah, so that is... now, the situation here is now that if we now count our total possibilities, we have symmetry-wise, yeah? I mean, we're now all set. Everything is now exhausted. Then we can draw or formulate a table which has 10 entries, not 9, but 10. And so let's now put everything together. What kind of possibilities do we have? We have the T-symmetry classes and the C category. But now we also define S. And here we should distinguish plus minus 1 situation, and here also the plus minus 1 situation. And whenever these are both good symmetries, their combination will also be a good symmetry. No? So we call this S1. Yeah, this is an S1 setting. So the system has a time reversal, charge conjugation, and therefore also chiral symmetry. If this one here is a good symmetry, but this one is absent, S cannot be realized because this would spoil it, and the same in reverse. Plus minus 1. This is also certainly not a good symmetry. The interesting one, where we have to be a bit more careful, is possibility number 9 of our table, where this is absent and this is absent. And if these two are absent, you have a situation where the combination can still be a symmetry or not. Yeah, two symmetries can be individually absent, but their combination is a good symmetry. I'll give you an example later on. So here we have the situation that this is allowed. And that is the extra possibility which splits number 9 into 2 options. So now we have 10 different classes, 10 different situations to distinguish. Is that okay? Yeah, so this 10 is 3 times 3 plus 1. So this is in general and therefore also abstract ways introducing different possibilities. Now let me make a few practice comments, ideally making you sensitive to the way these symmetries appear in reality and in practice. And there are some loopholes and traps one should watch out for where symmetries are concerned, and one better know them. So I make a few remarks in this direction. And then means second lecture. I will motivate these symmetries in a less abstract and more, if you want, physical way, starting from a, if you want, many-body setting, second quantized perspective. And finally, we will see how this setting which we have interfaces with topology. I mean, as promised, I will not go into topology, but at least I will tell you where topology starts creeping in. Yeah? So that's the plan for the rest. So general remarks. On symmetries. Maybe I should start with this one. There is a vast language confusion out there. And it's really, it's really bugging me myself in my work, and everybody else probably as well. I mean, different people call different symmetries by different words. For example, when you talk to somebody and he or she will tell you, yeah, of course the system is particle hole symmetric. Particle hole, what does it mean? So depending on who you ask, you get totally random answers. Yeah? And particle hole symmetry is sometimes called charge conjugation symmetry particle hole or particle hole charge conjugation symmetry. It's a plethora of different name tags and namings around. And my experience, it's always a good idea when you start talking to somebody about symmetries, really nail it. I mean, go down to the very basic and force everybody to declare what they mean by symmetry, because I give you an example later on where you have confusion, one and the same superconducting systems. Some people will call particle hole symmetries and other symmetric, others will call charge conjugation symmetric, and there's total confusion. Yeah? This what I told you before has the advantage that it's unique. I mean, you have to talk a bit, but after you have to this level, there exists an anti-unitary with these and that properties, you have nailed it. It's important. Then we often have situations, and like I said in the beginning, it's becoming more and more important these days, where systems are not symmetric under an anti-unitary, but there exists a clever unitary such that the combination is a good symmetry. And I want to give you one example of that. System, the example is a bit old school, but it's not topological, but still it's a good example, can be symmetric under combinations of unitaries and anti-unitaries. And the example I want to mention is old, 86, Barry Robnik. The Barry phase Barry. And it's the following. Consider a very simple electronic system, maybe some nano-fabricated system, a billiard. Yeah? And the billiard should be symmetric in space, something like that. I mean, ideally symmetric relative to this axis here. Yeah? And to make the situation more interesting, we put the system into a magnetic field. And we now have a situation where time reversal is gone because you have a magnetic field around. And the parity symmetry, I mean the space reflection symmetry you had initially, is also spoiled now by the magnetic field. So the system is no longer in time reversal symmetric in the sense of our discussion, and I make it explicit, and also not parity symmetric, but it's invariant under the combination of the two. So how do we understand this? How do we formalize such a situation? In this case, we just introduced two coordinates, and we introduced a unitary space reflection operator, a unitary symmetry, R, acting in the real space basis just by inversion of the x coordinate, it's natural. And we have a Hamiltonian which in a user-friendly gauge, two-dimensional Hamiltonian assumes the form px squared plus py minus, or plus, no, minus b times x. So this is a good gauge for a static magnetic field of strength b, just by shifting the y-coordinate of momentum, plus some potential which depends on x and y. And now you can see what's going on, yeah? If you apply parity symmetry, this one here changes sign, but that's okay. We have a square. What spoils it is this one here, yeah, because this one changes, this one does not. If you apply time reversal, this one changes to -1, which is, again, okay, because you have a square. This one changes to -1. This one remains invariant, so here you have a problem again. And this one here is totally out of the picture because it's symmetric. Yeah, you see why, right? But if you apply both in succession, reflection and time reversal, you get just a good constellation of sign changes that drop out. So that's an example of a combination of two symmetries which work. Hmm?
This is related to the Chiral example before.
Yeah, but not really, because here it's symmetric under a unitary and an anti-unitary. In the Chiral example, we have two anti-unitaries combined. Yeah, but philosophically, it's such a. And these days, it's becoming very popular. Yeah, you take a solid with crystals, point group symmetries. I know nothing about, not much, and you combine them in all possible combinations. And this 10 I mentioned, I mean, the most gruesome table that is out there has 252 elements of different unitaries and anti-unitaries combined, and they are all somehow important. So obviously, it's getting more rich when you combine different types of symmetries, right? So now comes a very, very important one. Actually, how much? 2 minutes. So very, very important final remark. And this one is important because it's quite often confused at this point. The thing is that you can have a symmetry around, nominally, in your Hamiltonian, like time reversal. And for all practical purposes, your Hamiltonian behaves like a time reversal non-invariant system. Yeah? And that happens very, very often. And I want to explain to you why and what's going on. So it's not enough to formally identify a symmetry and find out that your Hamiltonian does the right thing. You have to think a little more before concluding that the symmetry is actually physically manifest and does something. And the situation is this. Suppose you have an Hamiltonian, yeah? And you write down this Hamiltonian on your computer, you get a matrix. So you have something like that. And now, you assume that, that's part of the game. Usually you have some unitaries around, which the Hamiltonian preserves. Otherwise, it's not a very interesting Hamiltonian. So there are some unitaries in the game, which, I mean, let's say H, U. So if that is the case, you usually go to irreps of this unitary. It means you go into block representations. Yeah? For example, if these are rotations, you would organize an angular momentum multiplets. Yeah, you block, diagonalize your Hamiltonian, and it assumes maybe this form. Here maybe a small block, and so on. Yeah. After you have done this. Now, suppose now, in addition, we have an anti-unitary in the game. There is an anti-unitary around, which does what it does according to our tables. And now you have to distinguish two fundamental options. If you now act with an anti-unitary, and it's a symmetry, it can decide either it acts in one block, which is to say that, remember this was complex conjugation times another unitary. This other unitary can act in one block, or it warps you from one block to another. The Hamiltonian will remain invariant, but you can, this invariance can mean that you swap, that you exchange blocks. Yeah. So, I mean, just you know, in this pattern of blocks, you can have a non-local situation where, and I give you an example. This would be my last or minus last 30 seconds, or you can have something like this. And if this here is realized, you have an anti-unitary symmetry, but you will never feel it physically. Because, you know, you apply your symmetry, and you go from one universe to the other. So here you have some universe, and here you have its time-reversed universe, and they don't talk to each other dynamically. They're decoupled. So in this situation, you have a formal symmetry, yes, but you will never see its physical consequences. And that happens very often. I mean, a concrete example is, it was mentioned before, it's graphene again. If you have a situation in graphene and you have these 2 points in the Brimmer zone where you have your Dirac cones, yeah? If you apply a time reversal operation, you send this momentum over here. Momentum gets reflected, and so you morph from this point here to that one. So your time reverse states live here. Yeah? And the Hamiltonian is time reversal symmetric. I mean, it's precisely why it has these 2 points. But unless you have dynamical scattering or interactions going on between these will be decoupled, these states. Yeah? The situation changes totally if you have some potential scattering going on between them, or maybe some interactions or whatever, in which case you no longer have this parity symmetry which underlies the structure, and basically have one big block to deal with. Yeah? That happens when you have scattering matrix elements here and here. And in that case, you have one big, if you want, block structure which cannot be longer simplified, and you have time reversal acting within it. And then you see the consequences of it. Is that clear? Yeah?
But I mean, it still puts restrictions on the 2 blocks, right? It would still put restrictions on the 2 blocks. For instance,
Yeah,
if I invert the mass in one, I have to invert it in the other.
Yeah, sure, but absolutely. But you will never see any physical consequence of it. I mean, there will not be some.
The full system is
Huh?
physical consequences that I have twice the same
No?
mass almost.
No, you don't. For example, tell me what observable you would probe. Huh? Now, okay, good. Now we can negotiate. You can say that ultimately the existence of this very structure is a consequence of time reversal that you had it. That's a valid argument. But what I want to say is you cannot say, if I give you an observable and you weakly break this time reversal invariance, yeah, you will drastically see the consequences if they are coupled, and you will not if they are decoupled. You can do, say, I mean, you know these words, you can do weak localization or quantum interference, and you will just not see the symmetry.
So it's about the weak, basically.
Yeah, okay. Maybe so, yeah, Tito's make great comments, so you see, this is the situation, but watch out for it, yeah? I mean, it has a, this, before one starts working with symmetry, one better understand this pattern, and it's usually not difficult. I mean, you just have to do a bit of bookkeeping. Yeah, good. So that's a good starting point to finish. Lecture 1, is there a question? Okay, good, thank you.